Today we're going to be starting Unit 12, Chapter 10B, the second half of Chapter 10. For the next few days, you're going to want to make sure that you have this worksheet, this Chapter 10.7 worksheet. We're going to use it both as notes and homework for the next about 4 days. So you want to make sure that you have that handy. It's available on Schoology. You can download it, you can print it. But this is where we're going to fill in our notes, and then you'll see that there are different sections like Part A, Part B, keeps going, and those are all going to be where your homework's going to come from for the next few days. So you want to make sure you have this. What I'm going to do is I'm actually going to start by just talking through a little bit about polar coordinates and what they are, and then we're going to get into graphing them and converting back and forth. So we're used to thinking about points, coordinate points, as rectangular or Cartesian points, where you have an x and you have a y value. X represents a horizontal distance or horizontal value. Y is a vertical distance or vertical value, and then that can give us any single point we want in our two-dimensional plane. So if I look at the point 2, 2, I have this point here, this pink point, that can be represented as the coordinate point with the Cartesian point values 2, 2, where I have it. X is 2 and a y is 2. But that's not the only system, that's not the only way I can represent those point values. The other way we can, the other system we can use is what we call polar coordinates. These give us a second way that we can represent everything in our plane. And so the way we represent polar, or the way we talk about polar coordinates, is we have an r and a theta. So essentially what we do is we have a radius, or we have a distance from the origin, and then we have an angle value, and this is the angle with the positive x-axis. So just like every other angle we've been talking about, especially when we did that whole trig day a couple months ago, that's that angle value we're looking at. And so what I can do is, instead of talking about a horizontal and a vertical value from the origin, I can talk about an angle made with that positive x-axis and a radius. So if I want to look at that point 2, 2 again, what I can do is I can say, okay, if I have my positive x-axis, if I go out to the terminal side of an angle that would go through that point, if I were to look at that angle would be pi over 4 radians, or 45 degrees. So I can say that that point, the rectangular point of 2, 2, I can say that has a polar angle value of pi over 4 radians, or 45 degrees. You can go back and forth. It just depends on the context of the problem, which one you would rather use. And then instead of talking about a x and a y value, what I can do is I can say, okay, if I were to do that straight line from the origin to that point, I want to know how far those two are away from each other. I want to know the radius of the circle that that's on. That's going to end up being a radius of 2 root 2. So rectangular coordinate point system, that's a 2, 2, x, y value, where I go 2 to the right, 2 up. In the polar coordinate system, what I'm doing is I'm doing a 45-degree angle from that positive x-axis, and then I'm moving a distance from the origin out to that point 2 root 2 units. So you can see when we draw in our polar grid, grid's not really the best word because grid usually implies rectangular, but this polar grid in here, what we have is we have these circles that are increasing in radius. So we have a circle of radius 1, circle of radius 1.5, circle of radius 2, and then we have these angle values that are coming out, like sort of like a spider web. So we have this, pi over 4, pi over 2, 3 pi over 4, pi, and then we have our pi's over 3 and our pi's over 6. I did those backwards, but we have these angle lines that are coming out, and you can see where all these intersections are, where those nice radii value and those nice angle values intersect. But this will also get me to every single point in my plane. Polar is really nice for certain functions. The equations in polar for certain functions are a lot nicer. So like if I wanted to talk about a circle whose radius is 3, and we could even center it at the origin to make things nicer for us. So I've got a circle whose radius 3. In rectangular coordinates, we would have, x squared plus y squared equals 9. Not a terrible equation. But in our polar coordinates, we would just have r equals 3. I want every single point that's 3 away from the origin. And that would give me my circle with a radius of 3. So polar is helpful for in simplifying equations for certain things. It just gives us another way to look at every single point in our plane. So we're going to go to that worksheet now. We're going to work through some problems. This right here is where we're going to track, these right here are where we're going to track our points for the homework sections that we're going to have assigned periodically. What we're going to do is we're going to start by graphing these 5 points. All right, and so when we graph these are all in polar, which means they all go r comma theta. But when we graph this, what you want to do is you want to find theta first. Okay, that's the first thing you want to do is you want to find theta first and then move out that radius value. All right, that's going to be a lot easier for you than trying to do the radius and then find your theta. Find your theta first and then the r value. So in point A, my theta is pi over 4 or 45 degrees. So that's going to be this entire line here, and it's actually going to go backwards as well. This whole line here is an angle of pi over 4. Now, typically we would think of just this piece here being that pi over 4, and it is. But what's going to happen is that's going to represent my positive radius values. Technically, a radius can't be negative. If you're talking about like a physical circle or a sphere or something that's, you're going to hold it, it's real, you can build it, you can't have a negative radius. But for us, we can have a negative r value. What it means is you would, instead of going in the standard direction on that angle line, we would go backwards. And we're going to look at that when we get to C and E. But this is my line, this is my angle, 45 degrees. All right, and what I want to do is from the origin, I want to go radius of 2 out. So from the origin, I start here. This would be 1 and then 2 out. So what I have is right here is my point A. There's point A. All right, point B, I have an angle of 2 pi over 3. So that's going to be, if I'm trying to find my pi's over 3, you can do this a couple different ways, but I know that this would be my pi line, that horizontal one, and I want to cut that into thirds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 spikes that fill up the top half of that circle. So I want the 8th one. 1, 2, 3, 4, 5, 6, 7, 8. So here's my 2 pi over 3 angle line. And I want to go to a radius of 4. So I can count 1, 2, 3, 4 circles out. And there's point B. Now, when we get to C, you'll see we have that radius that's a negative value. So I still want to start by finding my angle first. So my 270-degree angle, that's going to be this line right here, but technically I'm going to go all the way back. Now, if I am going to do a positive radius, what I'm going to do is I'm going to start and I'm going to count. I'm going to go 1, 2, 3. This is the point positive 3, comma 270 degrees. For us to have negative 3, comma 270, what we're going to do is we're going to go in the backwards direction. So instead of starting at the origin and moving in that down the negative down towards that south point, what we're going to do is we're going to go backwards. So we're going to go 1, 2, 3. That's going to give me my point C up there. All right, so it's a little strange. It does mean that our points are not unique. All right, I can take that point C and I can write it another way. Point C could also be written as a positive radius of 3 at an angle of 90 degrees. So unlike in our rectangular Cartesian point system, our x comma y point system, where points are unique, polar coordinates, when you have a point in polar coordinates, there is more than one way that you can write that polar coordinate system. You can write that point in that system by going from a positive radius to a negative radius and changing the angle, or by adding in extra rotations to your angle. All right, 30 degrees and then 390 degrees are going to put you in the same spot. So polar coordinates, the polar coordinate system is not unique in how we label our points. Now, we have 2 more points to do. Point D is at 1 comma negative 5 pi over 4. Negative angle value means we're going to open up in that negative direction. We're going to go in that clockwise direction from that positive x-axis. This is a little bit over negative pi, so it's negative pi and 1/4 more. So that's going to give me this line right here. All right, so I'm opening up this way. That's at negative pi over 4. And I want to go a radius of 1, positive 1, which is going to give me this point right here. That's my point D. And then our last point, point E, negative 180 degrees. That's going to put me here. That's my negative 180. But I want to do a radius of negative 2. So instead of going to the left, instead of going out to that terminal angle side, we're going to go in the opposite direction, 2, which gives me my point E right here. All right, so remember, with those negative radii, you find your angle first, but now you're going in the backwards direction, which is why we want to really find that angle first and then our radius value. Angle needs to come first and then your radius. All right, so this part A right here, this is the first part of your homework. Okay, so you're going to work through these 4 problems right here. For the first part of your homework, you have more, don't worry, it's not just the first 4. What we're going to do is we're going to talk about converting back and forth between rectangular coordinates, the Cartesian coordinate system, and our polar coordinates, because we do have a connection between both of those. All right, so if you think back to that day, I think it was like in October, where we went through pretty much all of right triangle trig in one day, you would remember that, okay, to get points on these circles, you can draw on these right triangles here, where here you have some point. You can write it as x comma y. If we write it as x comma y, then the horizontal leg, this leg right here is my x. My vertical leg is my y, and we said r was the radius of our circle. It's also the hypotenuse of that right triangle. And in that right triangle, we have an angle, which we're going to call theta. And then we have our, all students take calculus, which we wrote over and over again to help us remind us our sine, cosine, tangent, which were positive, but that had to do essentially with x's matching with cosine, y matching with sines, where x and y are positive. But it does give us a connection to go from our x comma y points back and forth to our, r comma theta. All right, because I have this relationship between x, y, and r in my right triangle with theta, I know that if I were to take cosine of theta, that would have to equal x over r, my adjacent over my hypotenuse. That's just your SOHCAHTOA working right there. But that means x has to equal r cosine theta. So if I had a point in polar coordinates, say 2 comma 30 degrees, I could figure out what my x value was by doing 2, my radius, times cosine of 30, my theta. That would give me my x value. I also know that sine of theta has to equal y over r. Sine is opposite over hypotenuse, which means y is equal to r times sine of theta. So again, if I know a point in polar, I can figure out what my y value has to be by doing this relationship here. Now, if I know, say, a point in Cartesian, my x comma y value, and I wanted to convert it into r's and thetas, well, I do know that tangent of theta has to equal y over x. Tangent is opposite over adjacent, which means if I wanted to solve that for theta, theta is going to equal tangent inverse of y over x. Now you do need to be careful with which coordinate, excuse me, for which quadrant you're in. If you have a point down in the third quadrant there, your calculator is going to spit out an angle value that's in your first quadrant because of how tangent inverse is defined, how it's restricted to the first and fourth quadrant. So you just have to be careful that you're making sure that when you do those conversions that you put yourself back in the correct quadrant. All right. There's some other relationships. We have x, we have y, we have r, all working together in a right triangle. Right triangles, Pythagorean theorem always works for them. So that means if I were to take x squared plus y squared, I have to get r squared back. So this right here, this is if I have x and y, it's going to help me find my theta, my angle value. If I have x and y, this is going to help me find my radius, my r value. All right. Looking at this, we can see some of the other things. Remember x squared, or x was our r cosine theta, or I could write x squared over r squared plus y squared over r squared equals 1, dividing both sides by my radius squared. Or this is x over r squared plus y over r squared equals 1. That's just saying, all right, well, this is cosine theta squared, because we just said cosine of theta was x over r, plus sine squared, that has to equal 1. That's another way that we can show that Pythagorean identity is also valid. Now, taking this right here, this x squared plus y squared equals r squared, that does imply one more thing, that r is going to equal the square root of x squared plus y squared. Again, just knowing that if you wanted to using negative r, you would have to change your angle value and going back and forth. But these are the relationships that we have. So the big relationships are x equals r cosine theta, y equals r sine theta. I'm going to leave it this way, and knowing that we can solve for theta by doing tangent inverse, that just makes a little bit more sense for me. And then this x squared plus y squared equals r squared. That's how this is what we're going to use to go back and forth from polar to Cartesian and Cartesian to polar. Okay. Now, number 5 is also some of your homework. You're doing some more plotting like we did up above. And then 6 through 14, 6 through 10, what you're going to do is you're going to write different points that are the same location, just a different way to write it. So either by changing the radius, the angle, so making a negative radius, changing your angle value, or changing your angle value and keeping a positive radius. And then 11 through 14, what you're doing is you're converting those 4 points into Cartesian, the rectangular coordinate points. So changing those r thetas into x, y's using what we just did up above. Now, we are also today going to cover the part 2 notes. So part 2 notes have to do with, we're going to actually convert equations, not just points, but equations. So looking here, we can have our Cartesian points, our x comma y values. This implies that there is some function or some equation, f of x, which is equal to y. I plug in an x value, I get a y value back. And we can write this as an equation, f of x equals, or y equals something. So our line equations, y equals mx plus bu, or our parabolas, y equals ax squared plus bx plus c. We can write some equations this way. If I have polar coordinates, r comma theta, that is going to imply I have some function of theta or some equation r equals. So I talked about the circle. You can write a circle as r equals a value, r equals 3 for a circle of radius 3, or r equals 10 for a circle of radius 10. If we're dealing with our Cartesian system, all right, when we write the equation, we want to write the equation as either y equals something or in whatever is the best graphing form. So think about a circle. When we do an equation of the circle in Cartesian coordinate system, we don't write y equals plus or minus the square root of blah, 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 blah. We write it as, x minus h squared plus y minus k squared equals r squared. So there are some equations where it's a little bit easier, a little bit better if we write our equation in a different form, like circles or ellipses, those sorts of things. If it's an equation or if it's a function or if it's a graph that doesn't have a best graphing form like that, we like to have it, or we consider it to be simplified when we write y equals. The same thing follows for polar. For polar, we want to write our equations as r equals something. That's what we would consider to be simplified. R equals something, or in best graphing form. So if I'm thinking about, I want a line. I want, say, the line x equals y, but I want it in polar coordinates. That's going to be my line theta equals 45 degrees. I can't write that as r equals something. So this would be my best graphing form. This would be simplified. All right, so we're going to do a couple examples. We have 5 examples. There's not a whole lot of space here, so you just want to make sure that you write small enough that you can fit them all in there. They will all fit. I just wouldn't use the whole space for one example. But we're going to do some examples where we convert back and forth between polar and Cartesian and polar. Most of these are going to be going from Cartesian to polar, but not all of them. So this first one here, we are going to start with the equation y equals 3. All right, that is a horizontal line going through the point 0, 3. What we want to do is we want to convert this into our polar coordinates. So what we want to do is we want to take what we know y has to equal, and we want to do substitution. So we know from up above, from the page before, that y is equal to r times sine of theta. So in this example, instead of using y is equal to 3, what we're going to do is we're going to substitute in r times sine of theta for y, and now we have this equation. R times sine of theta is equal to 3. And what we want to do is want to simplify this. We want to solve for r. So to do that, we're going to divide both sides by sine of theta. So we get the equation r equals 3 divided by sine of theta. And this right here is that horizontal line passing through that point right there up at the top there. So all we did was, it's the same graph. We haven't changed the graph. We just changed how we're representing it. Instead of Cartesian variables, our x, y values, we're using polar coordinates, our r and our theta values. Okay, so that's our first example. Example number 2, we're going to start, it is another line. This line is 2x minus y minus 3 equals 0. This is also a line. If I were to sketch this line right here, this line is going to go through the point down at -3, and we have a slope of 2. So it looks something like this. This is this line. What we're going to do is we're going to rewrite that equation, but we're going to put it into polar coordinates. So what we're going to do is we're going to do the same thing. We're going to substitute what we know for x and what we know for y. X, I know from the page before, is r times cosine theta. And y is r times sine of theta. So now I have this right here. So we have done that conversion. We have now converted into r's and thetas. We don't have any x's, we don't have any y's anymore. All we left are r's and thetas. Those are our two variables. What we want to do is we just want to simplify. We want to solve this for r. So what I'm going to do is I'm going to factor an r out of my first two terms here. So I have r times 2 cosine theta minus sine theta. And I'm going to add 3 to both sides. So this is now equal to 3. And now to get r alone, I'm just going to divide. So my r is equal to 3 divided by 2 cosine theta minus sine theta. And that's my polar equation for my line here. And you may be thinking to yourself that that is not simpler, that is not a lot nicer, that's actually a little bit more complicated. Generally for lines, Cartesian coordinate system, the XY coordinate system, is simpler to represent a line. It's more of those curved objects, you know, those circles, those conics, that polar tends to be a little bit easier, a little bit simpler to work with. But we have 3 more examples. Our next example, example 3, we're going to start with a polar equation. We're going to start with the polar equation theta equals pi over 4. And what I want to do is I want to be able to rewrite this as an x comma y equation, and I want to be able to sketch the picture. Now, you might not be able to sketch the picture right away. Some of you might be able to say, I know exactly what that looks like, but some of you might have a little bit harder time with that. But what we're going to do is we're going to convert this, and then we'll sketch the picture. So what I want to do is I don't have any radius. I don't have an r value, which means my r value can be anything it wants in this. So I want to avoid the relationship between x and y that involve an r. So that y equals r sine theta or x equals r cosine theta. I don't really want to use that here because I don't have an r to use. What I want to use instead is the one that says tangent theta has to equal x over y. So what I can say is well, tangent pi over 4 has to equal x over y. But tangent of pi over 4 is just 1, so 1 has to equal x over y. This gives me the y equals x line equation, which, if I were to do a quick little sketch of that, which makes that vertical line nice and straight, is just this line right here, which some of you may have known right away, that is the line where I have that angle of pi over 4. So not every line is more complicated in polar, but most lines are. So that theta line, any line that goes through the origin and has that nice angle is going to be pretty easy to write in polar. But we can convert it to our rectangular as well. All right, 2 more to go. Example 4. We're starting with r equals 4, and we already kind of talked about what this looks like. Okay, r equals 4, we said that that's a circle with that radius of 4, so this is a circle with a radius of 4. To do that conversion, though, I just essentially want to use the relationship that says x plus y squared has to equal r squared. So this is just saying, okay, x squared plus y squared has to equal 4 squared, or x squared plus y squared equals 16. So this is that circle with a radius of 4. So if we did a quick little sketch, it's going to be centered at the origin. The origin there. All right, last example, example number 5. Again, we're going to start with a polar equation. So r equals -4 cosine theta. All right. Now, this one might be you might be like, oh, well, there's an x and an r and a cosine relationship, but that's x equals r cosine theta. R is multiplying by cosine theta. We don't have that here, so we can't just go straight to saying, well, x equals -4 or whatever it is. But I do want to use that relationship. I want to use the relationship that says cosine theta equals x over r. Okay, so just tweaking the x equals r cosine theta relationship a little bit. And we're going to do a substitution because I do want to get rid of my theta and get rid of my r if possible. I might not be able to get rid of them both at the same time, but I can start by getting rid of that cosine theta, and I can say, well, this means r equals -4 times x over r. And then if I multiply both sides by r squared equals -4 times x. But we have another relationship. We have an x squared plus y squared equals r squared relationship. Remember, x, y, and r all came from that right triangle. So this r squared here, we can replace that and get x squared plus y squared equals -4x. And we just got rid of all of our polar. Now, we haven't quite simplified it. You know, number 3, we got y equals. Number 4, we left it in the best graphing form, the equation of the circle. Number 5, I don't necessarily want to get y equals because the fact that both an x and a y are being squared tells me this is probably either a circle or an ellipse of some sort. But what I want to do is I want to get this in my best graphing form. So I'm going to add 4x to both sides. So I get x squared plus 4x plus y squared equals 0. And then by completing the square, I'm going to skip it because you guys are all experts in completing the square at this point. But if we complete the square, we get x plus 2 squared plus y squared equals 4. So this is a circle. Now, it is not a circle like number 4. Example 4 was a circle. Number 4 was a circle centered at the origin. Number 5 is a circle whose center is at -2, 0 in the Cartesian coordinate plane. So here's my center with a radius of 2. That's my circle down here. Notice how my polar equation is no longer r equals a number. So for circles centered at the origin, r equals 4, r equals 10, r equals 7. Those are nice values. Those are circles centered at the origin. If I have a circle centered off of my origin, that's going to introduce a cosine or a sine or some other trig equation in there. Okay, so that is it for the notes. The rest down until you get to the part where it says part C is homework. So 1 through number 10 is all of your homework. In class, we're going to talk about grading it, getting points for it, and getting those points to me, all right, or to Mr. Blake. If you have any questions,